Good morning. So this poster presentation is about a new tangential gamma ray spectrometer which has been developed at the Joint European Torus, mostly for fast ion measurements in deuterium and deuterium-tritium plasmas. This is the work from quite a large number of people, which you find listed here. So first of all, why do we want to have a gamma ray spectrometer? Well, at JAT, this is not the only gamma ray spectrometer available. There are also others. And the feature of this particular gamma ray spectrometer is that it is tangential. And in general, you want to have gamma ray spectrometer if you want to measure MeV range particles. These could be ions, for example, from radio frequency heating or the fusion-borne products, or this could also be runaway electrons. They both emit gamma rays for different reasons. The ions produce gamma rays because of nuclear reaction with impurity, and at JAT, the most important impurity is beryllium-9. Runaway emit gamma rays, or we should have to say MeV range Ardex rays, because of Bremsstrahlung with the bark plasma. Now, the detector we have developed is based on a lanthanum bromide crystal, and it exploits the successful experience of a previous device we had on a vertical line of sight. The way the signal is digitized is quite standard nowadays. So we have a photomultiplier tube, we have some U-metal, which is used to protect from some residual magnetic fields that we have at the position of installation. And we have a 400 megahertz digital data acquisition, which is used to digitize the signals from this instrument. And in order to build the spectrum, so we do a pulse height processing, and in order to build the spectrum, the energy spectrum of the gamma rays, we apply post-processing code. Now, the most important feature of this type of instruments is that they have megahertz counter rate capability. So you might ask yourselves, why do we need megahertz counter rate capability? Well, if we want to measure gamma rays from reaction produced by MeV range ions, we need the megahertz counter rate capabilities because in DT plasma, we will have significant neutron emission. And neutrons produce a background on the gamma ray detector, which could be in the megahertz range. And of course, we want to be able to still perform measurements under this severe background. And that's why we need megahertz counter rate capabilities. When it comes to the studies of runaways, we need megahertz counter rate capabilities. As in runaway experiments, particularly in post-disruption experiments, we have significant emission in a very short time. And typically, the rates from the Bremsstrahlung the runaways provide is of the order of some megahertz. And we want to be able to measure the spectrum with the instruments in order to tell, for example, the properties of the runaway distribution function. Now, as said, the technology that we have used is not completely new. I mean, it is now established since probably 10 years. But the peculiarity of this detector is that it is tangential. So here you see the detector line of sight in a view of the tokamak from the top. And here you see the line of sight in the colloidal plane. So you can see that this line of sight is a double pass through the plasma core. It is about 30 centimeters below the magnetic axis. And the line of sight makes an angle of 30 degrees with respect to the magnetic field in the core. And this is quite some implications on the capability to diagnose the fast ion velocity space, as we will see later. So why do we need a tangential line of sight? For example, there is plenty of experiments where the ICRH, or the power deposition, is off axis, where in general the generation of fast ions or runaway electrons is off axis. At JET, we have vertical instrument. We also have a vertical spectrometer. But what you can see is that if we have generation of fast ions or runaway electrons off axis, then of course we miss the signal from this. And that's why we need a tangential spectrometer. And this is the main reason why this spectrometer was installed. Another important feature of this detector is that it has a dedicated lithium hydride attenuator. If you don't use this particular attenuator, then the rates due to neutron background in deuterium-tritium plasma, the projected rates would be of tens of megahertz, and under this irradiation, this background, the instrument would not work. And for this reason, you need to develop a dedicated attenuator, and this is a very effective attenuator as described in this paper. Now, another peculiarity of this detector comes from the fact that its angle with respect to the magnetic field in the core is of 30 degrees. So what I'm showing here is the sensitivity to, for example, the alpha particle phase space. If you have a vertical view, a view that makes 90-degree angle with respect to the magnetic field, or if you have a view, which I call tangential here, which makes an angle of 30 degrees with respect to the magnetic field. So what I'm showing here is the part is the velocity space, the part of the velocity space of the alpha particles you are sensitive. If you measure this particular peak from this gamma ray emitting reaction, this is a reaction between alpha and beryllium producing neutron, a carbon-12, and gamma rays from the de-excitation of carbon-12. And if you measure events in the core of the line, of this particular line, at the edge, in particular here of the line, and here in particular we are considering 90 kV to the right of this particular line. So what you see is that if you have a vertical loss, a vertical line of sight, you are mostly sensitive to ions that, as you move to the edges, to the tail of the peak, you're mostly sensitive to ions which are trapped. While if you have a tangential loss, as you move to the tail of the peak, you are mostly sensitive to ions which are passing. So the other feature of having a tangential line of sight that makes an angle of 30 degrees with respect to the magnetic field, besides the capability to measure in cases where the generation of fast ions and runaway electrons is off axis, is also that you are sensitive to different particle topologies. So far I've motivated why the detector has been installed, what are its peculiarities, and now I should demonstrate that the detector actually works. And in order to demonstrate this, I'm showing you an example of measurements in recent experiment which pertain to the so-called three-ion scenario. So what is a three-ion scenario? Three-ion scenario radio frequency experiment is a relatively novel, it's probably 5 years old, relatively novel scheme to effectively couple power in the plasma core. And in this particular experiment I want to tell you about, we had the plasma which was made of deuterium and helium-3, and we were placing the power in the core where a neutral a beam of deuterium was picking up the power, and from its in this way, from its injection energy of 100 kV, the beam of deuterium would become energetic in the MeV range. So if we have MeV range neutrons, then we expect to boost the D plus helium-3 fusion reaction, and therefore to having in the plasma MeV range neutrons, which we accelerate radio frequency heating, as well as fusion-born alpha particle from the D plus helium-3 fusion reaction. Now, of course, in this type of experiment, we always have the vertical spectrometer. We measure a number, which measures the number of lines. They come from MeV range neutrons, which you see here, as well as from fusion-born alpha particle, which you see here. So the very fact that we observe these lines is confirming that in the plasma we produce neutrons as well as alpha particles. And we can compare what happens with the measurement that we make with this tangential spectrometer. So if you look in this region, say below 10 MeV, particularly in the range between 3 to 5, you can see that you basically, this is a little bit, it's not very zoomed, but you can see that we measure the same structures that we have on the vertical spectrometer. But another peculiar feature of this instrument is that its efficiency does not decay as a function of energy. So it makes sense, as we've done in this graph, which is a gamma ray spectrum, to consider what happens in a logarithmic scale and to consider particularly events in the high energy range. Now, if you look at this high energy range, you see that there are clearly events which stand out well above the expected level from the neutron background. And these particular events are due to one, let's say, one minor branch of the D plus helium-3 fusion reaction. So you're certainly familiar to the fact that D plus helium-3 fusion reaction produces alpha particles as well as protons, but it can also, with a probability of 10 to the minus 4, 10 to the minus 5, produce a lithium-5 and a gamma. And this gamma has an energy of 16.4 MeV, and when this is produced, it would show up in this region. And this is produced only if this D plus helium-3 fusion reaction is ongoing, which means that the very fact that we measure this component is telling us that this fusion reaction is ongoing. So I hope that by this presentation, I have convinced you that we have developed a useful instrument for JET. It is certainly complementary to the one we already have on the vertical anode side. It provides very useful information, and it does work, as we've seen recently in our experiments.